So here we have a graph that plots the potential energy of a 3 kilogram mass. And we are to find the stable equilibrium, the unstable equilibrium, maximum speed it reaches, the estimated force on the object at position -1, and finally the turning points. So first thing is labeling the stable equilibria. So stable equilibria is any point where if the object is to have any force exerted on it, it will return back to its original position. So therefore, we would label point right here as a stable equilibria, as well as a point right here, stable equilibria. So if an object were to be positioned here and a force was applied to it, it would continue to move back and forth and then reside right back to its original point. So then we need to label our unstable equilibrium. And on this diagram here, there's only one, and it's right here. So here the object is in equilibrium, but if a force were to be applied to it, it would eventually come to a stable equilibrium. So it would not return back to its original origin. Now we need to find the maximum speed that the object reaches. So the maximum speed will be where all the potential energy has been converted into kinetic energy. So we're looking we're looking for potential energy has been converted to kinetic energy. So on this diagram, that point is here. So we can label that as x equals 5. And what has happened here is this object had a potential energy of 15 joules, and it dropped, and all that has been converted into kinetic energy here. Therefore we label 5 as the maximum speed. So now we need to find we need to estimate the force when the object is at position -1. So -1 is about here. So here we go, right here. So what we need to do is, we know that change in energy equals force times distance. Therefore, force equals the change in energy over the change in distance. So we can use this to find our force equals. So all we have to do here is find the slope of the line, which will give us the force acting on the object. So we go force equals the change in energy. So we go from 10, let's go 10 minus 5 joules, so 10 minus 5 joules, over our change in distance. So we'll go from -1 minus 0. -1 meters minus 0 meters. And so this is your typical rise over run. So anyways, we come to our force equaling a -5 joules. Now we need to find the turning points. If the object has a speed of 2 meters per second at the origin, so here, if we have a 2 meter per second velocity, you want to find the turning points where it'll come back and continue to return back and forth. Assuming that there's no gravity, it would continue on forever. So what we do is to find the turning point, we can go kinetic energy equals half mass velocity squared. So our kinetic energy equals 1/2 mass of 3 kilograms, velocity of 2. So we go kinetic energy equals 1/2 times 3 times 4, or we get a kinetic energy of 6 joules. So what that means is, at this point, it has 6 joules, meaning that it can climb higher, it can climb 6 joules higher than 5. So I'll cross this line here. You can obtain a position of 6 joules higher on either side. So what we're saying here is, if we take our 5 joules, and we add it to our 6 joules that we just found here, we get 11 joules, meaning that wherever on the graph that the joules equals 11, so here and here will be the turning points, meaning that it'll continue here and it'll stop, return back, and hit to this 11, stop, and return back, and it'll continue on. So wherever joules equal 11. So here and here. And there you have it.